Hi, I am Gino Park. Today I will be presenting about TopFull, an adaptive top-down overload control for SLO-Oriented microservices. This work is done together with Jaeyoung Park, Youngmok Jung, Hee-jun Lim, Hyunho Yeo, and my advisor Dong-soo Han from KAIST. Hyunho is currently at Moloko. Microservice has become a de facto architecture of many service applications, thanks to its strengths in management and ease of gradual software development. In huge services, number of microservices go up to hundreds to thousands, like Amazon and Netflix in right bottom examples. So this is one example of microservice application, an open source demo app from Google, Online Boutique. Microservice application is designed as a collection of loosely coupled services. The picture shows a capture of Online Boutique webpage. From the webpage, users invoke various REST APIs, such as post-checkout, get product, postcard, and etc. They often require us to operate with service-level objectives such as end-to-end latency. When a user request arrives, it travels through microservices. Let me give an example with post-checkout API request. Post-checkout API is triggered when user clicks on Place Order. Request will first be received at front end, then it will trigger recommendation, checkout, card services, and furthermore. Once the successful response is built, this result is returned to the user. A different API request travels different path. This is an example of GetProduct API request. It will first pass front end and to the other services, and so on. Now, I'll briefly explain how overload causes goodput degradation. Before starting, what is goodput? Goodput is a throughput of requests that has been successfully responded within a predefined latency SLO. So when microservice application is at normal state without any troubles, end-to-end latency of every responses would fall within SLO. Thereby, goodput equals incoming rate at the entry. However, when overload takes place, some of the underlying services will have not enough resources to process increased requests. The queue will build up and the delay at services would increase. Every request would be affected by such latency elongation, and goodput degrades significantly. Before the overload, goodput was 100 RPS, but now it dropped to 5. With an appropriate load control, we can prevent such goodput degradation. Load control will shed admitted requests according to current resources and services. For example, when we admit requests at rate of 160 RPS, their end-to-end latency would satisfy SLO, resulting in goodput of 160 RPS. Then, how does existing work perform load control? Existing approach resolves overload by service-level load control. In Dagger, for example, it utilizes queuing delay at individual microservice and adaptively adjusts admitted rates until current queuing delay meets the target queuing delay. Per-service load control utilizes local observations and make load control decisions at each individual services. This comes with two advantages. First is the fast reaction speed, and second is that load control is decoupled from service logic, the APIs. Therefore, it isn't affected by service dependencies and robust even if there are flawed implementations in services. However, such approach lacks global visibility and suffers from two key limitations. First, API agnostic per service load control results suboptimal decision. Second, mitigating overload at individual microservices does not guarantee end-to-end maximal goodput. Let me elaborate this one by one. Let's assume a scenario where post-checkout and get-product API requests are arriving, and recommendation and checkout services are experiencing overloads. The first limitation happens when an API experiences multiple overloads on its execution path, and when there is another API also passing by any one of the overloaded services, which is very common since microservices are commonly utilized by many different APIs. For the simplicity, let's erase all the services except for the overloaded microservices. So this is what it looks like. Post-checkout API utilizing recommendation and checkout services, and get-product API utilizing recommendation. Existing approach would perform per-service load control, which will indiscriminately load control in API agnostic way at each service. From 100%, they will lower the admission rate until service does not experience overload. So here's the result, where recommendation service set with admission rate 50% and checkout service set by 30%. The resulting admission rate would process 5K of post-checkout requests and 5K of GET product requests at recommendation service, and checkout service would process 3K of post-checkout requests. At the end of the day, total served post-checkout requests would be 3K and GET product requests would be 5K. But in this simple example, we can easily calculate that we could serve 2K more GET product requests without any trade-off. Since post-checkout request is bottlenecked by checkout service, rather than admitting 5K of post-checkout requests at recommendation, we can just admit 3K. Then we can utilize the saved resources for serving more GET product requests. Now, the second key limitation is the mitigating overload that individual microservices does not guarantee maximal throughput. For the illustration, here is postcard request that first calls product catalog service, receives and response, then call cart service. Let's say product catalog service is experiencing overload, where existing approach detects them by local observations. They will load control until the monitored measurements satisfy predefined thresholds. Such approach will satisfy local conditions at individual service. However, the API's request end-to-end latency is accumulated along its execution path. In this case, latency of postcard request is accumulated sum of product catalog and cart. And as we can see, the latency characteristics of each services are complex and different from each other. And even if a microservice is not identified as overloaded, its latency can vary according to the sufficiency of current resources it has. Therefore, the optimal admitted rate to maximize throughput also varies depending on every microservice's condition on its execution path. Solving those limitations, we present TopFull. We solve first limitation by designing adaptive API-wise load control, which has the drawback of resolving overload microservice sequentially, so we solve this by designing parallel load control at each cluster. Next, we solve second limitation with RL-based rate controllers at entry with end-to-end observations. Let me start by introducing adaptive API-wise load control. Now we know that API-agnostic service level load control results suboptimal decisions. But then, how do we find optimal admission rates for each APIs? To reach the optimal rates, there are two criteria to satisfy. First, an API's effective admission rate should match the lowest admission rate among bottleneck microservices. Second, competing APIs should exploit the benefits of the saved resources from the above. To meet criteria 1, we first want all the microservices to share the same admission rate, and we made design choice of adjusting admitted rates per API at entry, so the load control impacts all the microservices on its execution path. Now we have to find the lowest admission rate by load controlling APIs on entry. However, it is difficult to adjust multiple APIs concurrently and discern the specific impact of each API. Also, load control of an API influences the efficacy of load control for other competing APIs. So we chose to load control step by step sequentially, through choosing a target service one at a time, adaptively decreasing rates of corresponding APIs. Here is the illustrative example of its behavior. We first target a service to resolve overload, profile API's execution path that goes through the target service, adaptively decrease rates of corresponding APIs. Once the overload is resolved, utilization of recommendations would be at its full capacity. Now, we move on to the next overloaded microservice and iterate the previous steps of adaptively decreasing the corresponding APIs. In doing so, we lowered post-checkout request rate even further. As a result, utilization of recommendation will be lower than its full capacity. To compensate this, we satisfy criteria 2 by searching APIs for rate increase. First, we examine execution path of rate-limited APIs, post-checkout, and GET product. We identify which execution path contains overloaded service. Then we increase the rate of APIs that does not experience overload anymore, which is GET product. This will make recommendations utilization to the TopFull. As we iterate the procedures, finally we will serve 3K of post-checkout requests and 7K of GET product requests as in the Oracle example. However, there is one major drawback of our approach. When there are multiple overloaded services, represented as a red dot, time for load controlling grows respect to this number. as we target and resolve overloads sequentially. It becomes more problematic when the size of microservice application grows. To solve the problem, we have a design component for parallel load control. This component finds independent subsets within microservices by examining interdependencies between APIs. Here, we cluster APIs and perform previous API-wise load control in parallel manner at each cluster. Now then, when APIs are interdependent and when they are independent, although APIs share many common microservices on their execution path, we identify APIs as interdependent only when those common services are in bottleneck conditions. Like in this example of post-checkout and get product, they are currently independent to each other since they do not share any overloaded services. They will be clustered together if services like recommendation, product catalog, and cart are overloaded. Set of overloaded microservices changes affected by our load control itself. Also, it changes to things like additional resource allocation from an autoscaler. In such cases, it performs reclustering and maintains clusters granular as possible. From here, we'll introduce the TopFull's rate controller. We previously explained that overload mitigation at individual services does not lead to maximal throughput. Thereby, we want a rate controller that makes load control decisions according to end-to-end performance metrics. Moreover, existing approaches often have static load control policy that reacts to the overload with fixed step size. Default dagger decreases admission rate by 5% when overloaded and increases by 1% otherwise. The graph shows results while changing the step size parameters of dagger. When the step size is too small, it wouldn't be able to react fast enough towards severe overloads. Moreover, with autoscalers, it wouldn't be able to increase the rate fast enough even after the additional resources are allocated. On the other hand, when the step sizes are too big, the final values wouldn't converge. So we want to build a rate controller that can optimize throughput by utilizing end-to-end performance metrics, and also that can adjust the aggressiveness of rate control decisions according to the severity of overload. To meet the design requirements, we adopted RL-based rate controller. The state action reward is designed as followed. For the state, RL observes ratio of throughput to the current rate limit and the end-to-end percentile latency. Action is taken as multiplicative step size between minus 0.5 to 0.5, which adjusts current rate limits at the entry. Reward is defined as total throughput changes among APIs with a penalty term for violating a latency SLO. For the model, we have used PPO model. One drawback of adopting RL is that training a model in real world is too costly in both money and time. So, we adopt sim-to-real transfer learning. RL agent is first pre-trained in a graph simulator, where our simulator simulates directed acyclic graph representing execution path and nodes representing microservices. During the initial phase of the training, RL agent makes mostly random actions and collects very low reward throughout the episode. With this simple simulated environment, we train RL to learn basic sensible actions. Once it learns a base point model, we transfer the pre-trained model to the target microservice. Then fine-tune the transferred model to learn the application-specific characteristics. We implemented TopFull to operate on Kubernetes environment, and it is open sourced in our GitHub page. We also utilized various third-party frameworks for collecting various metrics. Now I will share evaluation results. We tested TopFull on open source benchmark, online boutique, and train ticket, which consists of 11 and 41 microservices each. This shows an end-to-end performance result of TopFull, Dagger, and Breakwater. Under an overload, TopFull achieves higher average throughput on every APIs compared to the baselines. The right graph shows timeline of aggregated total throughput of APIs, and TopFull achieves a higher throughput entire time. We also tested different severity of overloads by changing user demands. Overall, TopFull outperforms Dagger by 1.82 times and Breakwater by 2.26 times. Now we examine effectiveness of TopFull's three components one by one. This result shows its explicit gain of our API-wise load control. As we showed in previous examples with post-checkout and get product APIs, TopFull is capable of serving same rate of post-checkout API as Dagger, while it serves more get product API without any trade-off. This shows gain of parallel load control. For comparison, we disabled clustering, where TopFull would naively resolve overload microservices one by one. Up to 22.5% of throughput decreased without parallel load control. The gain of parallel load control is more significant in larger applications. Here, we compare RL and MIMD heuristics. RL is better at converging to optimal rates faster than MIMD. Results show up to 34.4% throughput decrease without RL. Lastly, we tested TopFull with Kubernetes Autoscaler. These results show performance gain from Autoscaler with TopFull compared to the Autoscaler solo. Under the overload, Autoscaler solo suffers transient performance degradation due to delays in resource provisioning. On the other hand, TopFull compensates transient overload and provides up to 3.91 times more average throughput. In conclusion, TopFull is the first API-wise load controller that utilizes the execution path of APIs to maximize total end-to-end throughput. Second, TopFull performs cluster-wise parallel load control upon APIs, which provides scalability to a size of microservice application. Third, we adopt an RL-based rate controller, which provides an adaptive rate control policy based on end-to-end performance observations. This is the end of my presentation, and thank you for listening to my talk.